Okay, welcome everyone. Our speaker today is Igor Pikovski of the Stevens Institute of Technology and Stockholm University. Igor studied at the Free University of Berlin and also at UCSB, then got his PhD at the University of Vienna, working with Czeslaw Bruckner. He was an ITAMP fellow at Harvard and joined the faculty at Stevens in 2018 and has had an affiliation with Stockholm since around that time as well. Igor works on quantum foundations, quantum sensing, quantum optomechanics, connections between quantum physics and gravity. If it's quantum, then he's interested in it. Now, at Caltech, we respect scientists who try to do things that seem to be impossible. And Igor is in that category, as his talk will demonstrate. Tomorrow at noon, he'll be giving another talk, the IQIM seminar, about testing quantum theory in curved space-time with atomic clocks. And as usual, we'll have a reception after the talk on the terrace at Bridge Annex, where you'll have an opportunity to chat with Igor some more. And now we will hear from him about demystifying graviton detection.
Let's see, this is the hardest part. I do theory, so this is not going to be easy. Okay. Does this work? Can you guys hear me? Okay, great. Yeah, thank you so much. Thank you, John, both for the very kind invitation and also very kind introduction. I hope the emphasis is on seem impossible on the first part, but we will see. And I'll try to at least convince you about the former. Now I want to say that I had a lot of fun here at Caltech now the last few days. So many wonderful discussions and interesting ideas, hearing from students and faculty. I also want to emphasize actually my personal journey also, at least remotely, went through Caltech a couple of times. As a teenager, I got really excited into physics after reading Kip Thorne's book on black holes and was it, I think, time, something about time. But it stuck with me, so this fascination with gravity. And then as an undergraduate student, I came across John's wonderful lecture notes on quantum information. And I thought this is the most amazing field I've seen, really remarkable, and so special that nobody's interested in. So I thought I'm going to go into this field. Now that changed after a while, but this connection stayed with me. And then finally, what brings me to this talk is actually also connection through Caltech with Keith Schwab. So about 8 years ago, me and Keith, we collaborated, as well as Swati Singh and his student Lorenza, because Keith built this wonderful system, the superfluid helium resonator, which was very massive, and it has a humongous Q factor. And she was asking me, well, if I have this huge Q factor, is there something about gravity that I could detect which is really new? So we had this paper about gravitational wave detection, but this question stayed with me. And in fact, it led to this thinking that actually, if you really have a resonator which doesn't do anything, it just doesn't dissipate, well, what if you wait until you see a quadrupole transition? Could you then detect gravitons? And it turns out, yes, you can. And it turns out it's pretty easy. It's really not that hard, compared at least to the theoretical predictions that we thought were there before. So that's what I want to convince you about in this talk. So hopefully, at least maybe there will be a good discussion, or even better, real experiments. I want to also give you a little bit of an overview of the field before I get started. So first of all, in my own research group, we study kind of the interface of quantum mechanics and gravity, and hopefully gravity is quantum, but we don't fully know. But one of the main interests that I have is to see how can we apply some of these quantum foundations principles to design experiments, that we can probe some basic principles about how gravity and quantum mechanics meet. Okay, so in my group, we explore ideas related just to regular quantum optics, quantum control of various systems, atoms, optomechanical systems, quantum sensing, and so forth. But then in particular, we're interested in how can we extract gravitational effects within quantum theory and maybe see some signatures or indirect signatures of quantum gravity with low energy precision experiments. Okay, so I mentioned this in particular because the main message is that we also have open positions. So if you know anybody who might be interested in doing research in this field, let them know to reach out. And we're located at Stevens, which is just across the Hudson River on the other side of Manhattan. So with beautiful views. Okay, now let me go back to about 10 years ago when I was finishing my PhD. I was trying to summarize in some form, zooming out in terms of what it is that this field is trying to achieve, and where is it exactly where experiments could fall. And so this is kind of the kind of cartoon picture I was thinking about at that time. Okay, let me see how the topology here is. Let me stand here. So this is just basically trying to summarize all of physics that we know in some category. So on the one hand, we have classical mechanics, which then over time, of course, became many different fields. Among them, Newtonian gravity is what we well understand. But there's other aspects of classical physics like electromagnetism. And then there were mergers. Like, oh, we could merge electromagnetism with our understanding of classical kinematics, leading to special relativity. But then, of course, there are more mergers, and in particular, the great insight of Einstein is how to merge relativistic principles with Newtonian gravity into a big new theory, general relativity. So this is our understanding of, at least, of gravity as it is today. On the other hand, we had a development in parallel for quantum mechanics, and there was a big merger with special relativity, which really could explain everything there is except gravity. So all the fundamental forces we currently understand as within the framework of quantum field theory. But there is a mismatch between we don't know fully how to quantize general relativity, and there's different aspects to it, how these two kind of blue, which is the quantum aspects, and red, which is the classical theories, meet. And here, just for clarity, general relativity essentially has like two different aspects to it in terms of phenomenology. One is how do test particles behave in the presence of curved spacetime, and the other is how does curved spacetime itself behave as a dynamical field. Okay, and so for one we need geodesic motion, for the other we need Einstein's equations. And now why this separation is useful, because it helps understand where it is that these theories meet. For example, there's this big field and big boom since the 70s about quantum field theory and curved spacetime, where we don't need the full theory of quantum gravity or even all of Einstein's equations, but we place quantum fields on a background, which is curved. And there's new effects that arise. There's surprises that arise, but there's ways to deal with all that mathematically without too much trouble, at least in principle. Okay, so this is this interface. But what I want to highlight is that there is also a low energy limit of that. And in particular, there is something like quantum mechanics on curved spacetime where you don't need field theory, because the test particles you're looking at are really just low energy systems, AMO precision experiments like atoms. Okay, in fact, not only do you not need field theory, it is probably a good idea not to use field theory, because it will not be able to describe these bound system, complicated systems, and the type of effects we're after, like entanglement or some kind of quantum features within low energy quantum physics. However, we can still couple these systems to gravity, and in particular, we can couple it to general relativity and see what novel effects arise. And this is what I call quantum mechanics on curved spacetime. Okay. Now there's another limit which we understand well, at least theoretically, and it is linearized quantum gravity. And that is taking this full theory of general relativity and just taking the linearized limit of it where the fields are not so strong. And then this theory looks a lot like Maxwell's equations with a few small differences, but in principle it's extremely similar to just electromagnetism. And one can also quantize it in principle. Okay, and so as long as there's no self-interactions of gravitons, it should describe physics well. Okay, so that's another limit. Now there is also other aspects which you might not know, and there is something which I call quantum gravity phenomenology, which is trying to incorporate maybe some expected feature of an underlying theory, which, however, change some of our current understanding. Okay, so there's quantum gravity phenomenology, which could incorporate certain principles which maybe break quantum mechanics or maybe break general relativity in some form, but it could predict certain, observable consequences. And then finally, of course, the ultimate goal is the full quantum theory of gravity. There's many contenders, and a lot of progress has been done over decades, string theory and maybe other attempts at loop quantum gravity, but there's no kind of full-fledged framework which is generally accepted and kind of can really describe everything currently in all its limits, at least not fully understood. Now, I'm putting this because what I want to say is that essentially what we're doing, or in general, maybe this field, I would say this low energy interface between quantum theory and gravity, is essentially focusing on these three aspects here. Quantum mechanics on curved spacetime, meaning you take clocks or atomic fountains, and then you see how gravity affects them. Quantum gravity phenomenology, where you look at maybe certain effects, you create superpositions, or maybe you look for some anomalous quantum noise or something like that, where maybe you expect some kind of new physics to arise, and also linearized quantum gravity. And that is really a prediction from kind of normal physics, but there could be hints of the quantization of gravity, even in the linearized limit, that could be accessible. So that's what we're interested in, to see about how can we access these things in experiments, at least in principle, and how to gear towards it to current capabilities. Okay, so let me first explain why this is possible in general. This is really very much driven and inspired by experiments. Sorry, I was blocking your view, but yeah, I can restart it. Okay, sorry. But it really is mainly inspired by actually this incredible experimental progress. And the experimental progress is not just simply, oh, there is some kind of improvement by many orders of magnitude of a system that we'll understand. It is rather the broad range of AMO systems that have really exploded in the last 20, 30 years, which allow us to ask different type of questions about the interface of gravity and quantum theory. Just to give you some example, one is, for example, atomic clocks that nobody needs convincing that these are incredibly precision tools, and in particular, they're sensitive to unique features of gravity, which is the bending of time dilation. And so what you see here is this ultimate precision, which is doubly exponentially improving over several decades, and now even with the new development of nuclear clocks, where there's just new capabilities arising where you can ask questions about fundamental physics. Another example is our atomic fountains, where you can take atoms and separate them across large distances, which are really macroscopic, meter scale or maybe even 10-meter scale superpositions of little atoms where, where really macroscopic scales, you can walk between them and they remain coherent. So this allows you to probe also novel features about where gravity meets quantum mechanics because of these large separation scales. And then as a third example is quantum optomechanics, which allows you to actually do quantum physics with macroscopic collective degrees of freedom, such as the center of mass modes of some resonators, like drum resonators or piezoelectric resonators, all the way even to LIGO mirrors, where there's now been demonstrated quantum effects, entanglement, phonons, ground state cooling, and even Fock state superposition sizes across mass scales, which are really macroscopic compared to the atomic scales. And so all these different developments allow you in principle to start asking certain specific questions. Not everything about how gravity affects these, but there's certain questions that then become accessible with these novel devices. And so this is really where the inspiration comes from, to ask theoretical questions about what can we learn when we add gravity in the right way to these type of systems. Okay, so So first, let me just say the following. There is actually no experimental evidence to most of these things that I mentioned here. And in particular, for example, even surprisingly, quantum mechanics on curved spacetime has never been probed. In other words, it could be that gravity is just in the quantum domain somehow is purely Newtonian, and somehow curved spacetime doesn't even couple to quantum systems, and it will be consistent with experiments. So there's no experimental evidence how really the Schrödinger equation has to deal with curved spacetime, and this is something I want to just briefly mention here and talk more about tomorrow. The only experimental evidence we have where gravity really has to matter in the quantum domain is from this type of experiment. Namely, experiment where you have some kind of quantum system and it experiences a quantized Hamiltonian due to the Newtonian gravitational potential. Okay, so in particular, this is well tested with so-called narrow wave interferometers, first done by Colilla, Overhauser, and Werner for neutron interferometers. What they realized is in 1975, 50 years ago, is that, oh, if you actually take a matter wave and you split it even, by just a few centimeters in the gravitational field, it will pick up a gravitational relative phase induced by the Newtonian potential. And why this is interesting is because here you really have to add the Newtonian Hamiltonian into the Schrödinger equation, because this really is a quantum coherent phase. Okay, it's not just simply dropping an atom. It really is a unique effect which cannot be described without quantum physics. Okay, and this is actually unique, routinely observed now in many systems. Here, first observation in 1975 with neutron interferometers in this like little interferometer that you can rotate with cold neutron beams. But then recently, for example, when Mark Kasevich's group or Holger Müller's group, many groups that really use atomic fountains and modern version of it, and also high precision sensors for gravitational constant G. Okay, so it becomes a sensor, but essentially what it probes is that the Newtonian potential, the influence of classical Newtonian gravitational field has to be added into the probe system, into its Schrödinger evolution. Okay, so what we basically know from experiments is that we must kind of quantize this Newtonian potential in terms of how it acts on a probe system, and that this induces a coherent quantum phase, okay, because it's a superposition of different heights. And it works in exactly the same way. There's nothing surprising, of course, about it, because any potential would do that. The only surprising part is that, well, we can actually see it for gravity too. And so gravity is no different at this limit. And that's okay. But what we don't know from these type of experiments is, first of all, what about really the metric nature of gravity? Gravity is actually not like other potentials. It really has unique features. And can we see those? And this is precisely the goal of seeing quantum theory on curved spacetime, where there are some post-Newtonian corrections that play a role. And this experiment doesn't tell us anything about quantization of gravity. Okay, and so there is a way to go beyond this and to really see in real realistic experiments in the near future to see how there is actually corrections which are unique to gravity, in particular related to time dilation, which would induce novel effects. And this is what I call proper time interferometry, and this allows you to test how quantum systems really behave in the presence of curved spacetime. And this goes back also to like initial ideas we had a while ago, and then more recently we had this extension to quantum networks, where we realized, oh, you can piggyback on the recent developments in quantum technologies to actually show that these experiments are now becoming really realistic. And this is in collaboration with many different people that we're exploring it. So this is just a quick summary, but I'll talk more about this research direction tomorrow in the IQIM talk. Okay, but again, this is not about quantum nature of gravity. This is rather about a quantum system, which is a probe of curved spacetime, and how these two things intertwine. Yet, there's no experimental evidence for that, even today. And so hopefully with these experiments, there will be soon some real input that, okay, things work at least as we expect. On the other hand, there could always be surprises. So it's worthwhile. Okay, now there is another aspect where experiments can add significantly to it, and this is that there could be potentially new physics, and the goal to exploring that is this field of quantum gravity phenomenology. And I just want to briefly mention that there's a lot of tabletop routes that have been suggested and performed probing this type of limit. Now, they're all null measurements until today. And so it basically means that, look, there's all these different ideas, but this is not actually exactly how physics works, at least as far as we know today. And so there's this ideas, for example, for Roger Penrose, that maybe gravity should not be quantized and instead causes wave function collapse. So there's a goals to test that. There's other ideas, for example, that maybe the uncertainty relationship is somehow modified, inspired a bit by ideas from string theory. There's ideas that maybe there's some fundamental noise. There's a lot of different ideas and geared experiments towards probing that. Okay. Now the caveat of that is that these experiments so far are null experiments. We could be lucky, we find something, then it's really new physics. But the caveat is that it's really speculative ideas. Okay, so most likely they're going to be null experiments. Still, this is experimental input. To me, this is not too different from like experimental input on, say, dark matter particles. That, okay, we know it's not a WIMP and it's not in this range, but okay, it gives some input. And here it's similar in terms of like, okay, there are all these ideas floating around and theories discussed. Is it a good idea or bad? But this is not so important, rather that, look, there's relatively simple experiments, not too expensive. Tabletop experiments can be done to actually provide input on this. Okay, so this is one aspect, and here I don't want to talk more about this direction, and there's interesting ideas here, but I just want to say this is one aspect of tabletop experiments that really can provide input. Now, let me move on to this third part, and this is really what I want to focus the rest of the talk about, and that is that we can actually probe also aspects of linearized quantum gravity. And one thing that is really kind of a key feature of linearized quantum gravity in most approaches. So whenever you quantize gravity, near certainly you will get one key feature, and that is that there should be a particle associated with it. Okay, this is the key feature of quantum mechanics. And this new particle is, of course, what we all know as the graviton, that it should exist. Okay, now before I get there, I want to say that there have been ideas floating around that have been quite popular and influential in the last 8 years or so, and they are about experiments trying to indirectly sense something about this linearized limit of quantum gravity. And what is there the basic idea? The basic idea of these experiments have been proposed by Sugata Bose and many collaborators, as well as Vlatko Vedral's group. It is to try and generate entanglement through gravity. Okay, so essentially, if you make big enough masses, they will gravitate, and then if you place them in superposition next to each other, could they generate entanglement? Okay, let me say just a couple of words on this. I don't want to spend too much time on it, but a little bit about, because this is really a popular subject in this field at the moment, and the argument goes something like this. The idea is, imagine we can make mesoscopic systems and really create superpositions of them. Say something like milligram or microgram spheres, we create them in superposition. Okay, and this is, by the way, way beyond what people can do currently, but it's still some mesoscopic scale somewhat. And the idea is the following from these papers, namely, look, this entanglement is generated through this Newtonian interaction. It's just Newtonian gravity. However, if we imagine that instead there is some underlying field theory that mediates this entanglement, that there is some kind of local mediator associated with it, well, then there is a fundamental concept in quantum information theory, which is just simply a definition. It's not even like a conjecture or something, it's just a definition. Namely, by definition, we know that any local operation, which is only a classical channel, will always stay within the space of separable states. That's essentially the definition of separable states. So if you want to go beyond separable states, entangled states, you can never be within this class of LOCC. Okay? And this is what they piggyback on. They say, look, this entanglement must be generated somehow. This is generated maybe by some local mediator in the field theory. And then if you see entanglement, well, that means this mediator must be a quantum system, because otherwise there would be no entanglement that's possible to be generated. And I just want to say this idea of essentially testing if gravity is an LOCC channel or a non-LOCC channel can be generalized. You don't even need entanglement. There are some recent ideas where maybe you can test for swaps. So we know that the swap is actually also outside the LOCC class, swapping arbitrary states. Okay, and yeah, that can only be done if it's a non-LOCC channel. And then also recently in my group, for example, we extended it to the idea of, we can also check instead if gravity can mediate a quantum memory coherently. Okay, and there the idea is to have maybe a very large system that you take away, and then next to it is just a small qubit, and you just essentially swap onto the large system, a quantum state, and then see at a later time that it can coherently come back. So there's like a very precise witness for quantum memory, and then this would allow you to basically probe also that this is non-LOCC channel. Okay, this is just to mention that there is these indirect questions of, is gravity an LOCC channel or not? And these, are very, very difficult experiments, but one can conceptually think about it. Now, the critical aspect here is, why is this Newtonian interaction a local operation? Okay, on the Newtonian level, obviously it's not. Okay, just directly couples those systems. Okay, and the idea there is there's an additional assumption here, that there must be some mediator associated with this force, and this must be some kind of local graviton or something like that. However, this is an ambiguous interpretation because it really requires a little bit more input. This has nothing to do with the experiment itself, and so you need additional assumptions that really there is some local mediator. And we looked at it actually quite carefully just to clarify, because all these debates, it's correct or not correct, kind of how does it actually work, and what assumptions do you need to make? And just on one slide, just as a quick summary, so this experiment, you'll see entanglement. And now comes the metaphysics beyond that, kind of what do you learn from it? And this is really very ambiguous depending on what is kind of your favorite description of what you just saw. If you just stick to Newtonian gravity, there's nothing really here local, and you don't learn anything about gravity itself because it doesn't even have any degrees of freedom. All you know is that these systems have sourced gravity in a superposition. This is actually not too different from what we already know from cosmology, because to explain this cosmological fluctuations, they do actually also have the scalar part of the gravitational field in this Mukhanov variables. So we kind of know, at least if we believe cosmology, that look, the gravitational scalar part of the potential is able to source gravity, at least with quantum fluctuations. Okay, but this is essentially what you would probe. And now, but what the argument here is, oh, well, no, but Newton physics is not right. We should go to field theory. And if we go to field theory, there's a way to describe it. Let me not go into, it's just you linearized gravity, and then you look at the interaction between the systems. And now the interpretation depends on what gauge is your favorite one. So it's a little bit ambiguous there too. You can describe it locally, indeed, that you have like a particle exchange, which is a virtual particle, and then the argument is indeed that now you have to quantize this particle, and this interaction looks, through these particles. Except these particles that do mediate the Newtonian potential are spin zero particles. They're virtual spin zero particles. They're never directly observable. They're not even the real gravitons. But okay, if you assume it must be the local gauge, then this is, then you must say that these particles are really there and you have to quantize them. Or you can describe it in a different way, still within field theory, and you can take a Coulomb gauge, and what you find is that there is actually a direct interaction term, even within field theory, between the distributed masses, so you don't even have any mediators in this picture. So like in another picture, there's no degrees of freedom, and so this entanglement is also generated locally. This is all to say that just this mechanism of how entanglement is generated, what people debate about a lot, is really kind of a little bit more metaphysical. It's not part of the experiment. It's just you have to impose some additional assumptions to learn something about the quantum nature of gravity from these experiments. And other people have pointed that out as well before. Okay, so I just want to say that, okay, this is just on this part, which is kind of, a big topic and a lot of people study it. It's an ambiguous interpretation. Yeah.
Can I just ask, so we just go back to the previous slide?
Yes.
To make sure I'm following.
Yeah.
So something I've heard many people say is, oh, if you do this experiment, like only, I think just exactly what you were saying, but I want to make sure I understand. Only if like gravity is quantized, is this possible? And you're saying that that's not true.
That's not true, right? This is not true.
This is what people say, and then
this is what people right. This is why some other people pointed it out. Also, like it's more careful than this. This is to say you see entanglement, and if you now assume that this entanglement must be generated by gravitational degrees of freedom, which are local, then it must be quantum. Okay. And this is bulletproof if you add this additional statement. However, our point is there's no reason for you to assume that in this experiment, because this is a gauge dependent statement that it's kind of like, what's the underlying mechanism? Because people like to say, look, we know physics is local. Okay, everybody accepts it. So obviously, there must be some local mechanism for it. But in field theory, the observables, of course, are local, and the observables are just the masses. But it doesn't mean that the underlying mechanism is just a mathematical tool to describe it either as virtual particles or in this non-local gauge. So there's an additional assumption here that you must impose that only one picture of field theory essentially is correct, and that's only the underlying local gauge essentially. So that's why it's not, and look, maybe that's correct, I don't know, but to me it's more like arguing if, I don't know, if many worlds in Copenhagen are right. I don't know. Like, it's not an experimental question. So this entanglement, you see that, and then if you associate with it some virtual mediators, then you must quantize them. And yeah, otherwise not. So there is some ambiguity in this argument. However, still, if this experiment is easy or possible to do, it would be great because you really see how you source gravity with a quantum superposition. It's just you have a little bit limited, I think, input on the quantum nature of the field theory. Okay, so I just want to say that this interpretation of that has some caveats. Okay, but what I want to say now is, especially in contrast to this, there is something that we recently proposed which has nothing to do with it. So I just want to kind of separate. Just as this phenomenological part has also nothing to do with that, it's a different aspect, a complementary one. Namely, what we realized and proposed is that you can actually also detect gravitons as predicted by field theory real on-shell gravitons, not virtual ones, directly. And it is actually possible. Okay, and so this type of experiment will be something different. This amounts to the observation essentially of the quantized exchange of energy between passing gravitational waves and a detector. Okay, so what this would do, such an experiment, if one can implement it, it would really probe this expected single graviton physics as is predicted by linearized quantum gravity. So one can zoom in on this limit and explore it and see if there might be surprises. There are caveats, and I'll say more about it in the end. Namely, this is not a full proof that somehow quantum gravity is correct, because there are also loopholes in this type of experiment, and in particular, there's some semi-classical models that could reproduce these type of effects too. So you could still live with not quantizing gravity, even though you see signatures of essentially single gravitons, because there is some loopholes. However, these are really kind of unusual semi-classical models. They're not normal wave physics anymore. So I'll say a little bit more words about this as well. Okay, so now let me zoom in on this kind of graviton detection. And I have to say, like, often it's treated, also for me, it's treated a little bit like a sacrilege. Like, how can you talk about this? Because, we all know it's not true. And there's extremely good reasons to know that it's not true. And they're right. I was thinking about it. I also thought there must be something wrong because, why should it work for like Keith's experiment? Somehow, like, there's something that must go wrong. But I want to go through kind of the arguments why people believe until now that graviton detection is really way outside of experimental capabilities. Okay, so there's, for example, one beautiful paper by Freeman Dyson, and he actually talked about it for many decades before as well, where he talked about, look, maybe it's like a no-go theorem. Maybe there's just no experiment ever that could be done to detect gravitons. Okay, and he has many, many examples in this paper where he showed, look, it just never works. One of them is like, look, let's try to really detect it. Let's try to absorb energy. Essentially, he finds, look, your detector has to be so big it just becomes a black hole, something like that. There is another two papers, actually very beautiful papers, fantastic papers by Tony Rothman and Stephen Bond. They were inspired by Dyson, even though they came 10 years before, but there was this discussions for a long time. They very carefully looked at this question of, can gravitons be detected, and exactly how do you describe it? Basically, just exactly how do you mathematically describe it, because it's within linearized quantum field theory that we can, gravity, that we can treat. And what they find is also here, this outcome is on Wikipedia also still, namely, essentially they confirm Dyson. They say it's never possible, and the only way to do it is you would need a detector of the mass of Jupiter, 100% efficiency, and it's literally next to a neutron star. And then if you wait 10 years, you'll see a click. Okay, so that's the outcome. And that sounds reasonable. Kind of feel like, yeah, that's how it should be. Okay, so then instead we come with our paper and say, oh no, actually, you know what? You only need 10 kilograms. You go to Keith Schwab's lab, 10 kilograms, and you should see it within a second. Okay, and then the first is like, okay, like, there's something wrong with this argument. However, I'm going to show you that it's the exact opposite. There's a reason for that, namely because these arguments are a little bit limited, and I'll show why. They're limited in terms of not the ideal detection technique. Okay, so in particular, before I get there, let me just say that what is the definition even of detection, okay? It has nothing with our paper, just in general. What do we even mean by particle detection? Okay, so you take Dyson's paper, for example, he said the simplest kind of the graviton detector is an electron in an atom. Okay, then we have a splendid generator of thermal gravitons from the sun, say. So there is some kind of source, which is classical. There is some detector, which is like an atom. And then what we use is the gravitoelectric effect. Okay, so essentially we use something like a photoelectric analogy that this atom is excited by the source, by just one quantum. Okay, very similarly in the Rothman-Bond, for example, let's use the gravitational analogy of the photoelectric effect as a method to detect gravitons. So this is just how detectors work. Okay, so we basically compute the gravito-ionization. So you take an atom, gravitational wave passes, and then maybe it will ionize your atom. And that would be one detection event. Okay, so in essence, what does it mean? We want to look at energy transitions of exactly one quanta, E equals HF. Okay, one quanta, this is precisely the atom that it does it. It gives you one quanta which is discretized, and you have a source which is classical. It's just thermal. Okay, so this is, it has nothing to do with the source. Particle detection has nothing to do with the source. Okay, so you extract it from some background. Okay, so this is just, this is just accepted. This is not something we impose. But even under these conditions, they find you can never do it. And this is kind of the standard thinking. Okay, so now let me zoom in a little bit more. Just how does the math look like? And I don't want to be too much over time. I just want to quickly run over it. There is a very beautiful and easy way to solve it, which is very analogous to quantum optics. And that is by using the Hamiltonian formulation. Essentially, in the linearized limit, we know the interaction Hamiltonian between the gravitational field and matter, and it's nearly identical to the electromagnetic one, except instead of a mu coupling to the velocity, we have t mu nu, which is the stress energy tensor, coupling to the gravitational field h mu nu. Okay, so this is this coupling Hamiltonian. Now, this Hamiltonian really just governs the interaction. This is the stress energy that it tells us basically our detector, and this is this metric perturbation, which could be gravitational waves, for example. Okay. Now the point is that in the linearized limit, we can find that this h mu nu obeys essentially the same as Maxwell's equations. And then in the source-free limit, you essentially just have free wave solutions, and you can quantize them if you want. You can essentially replace these Fourier components with hats. And then, there's this polarization tensor. So the only difference really is the kind of, the polarization compared to the electromagnetic field. And so essentially what you're saying is that, oh, look, these gravitational waves, I can also just make them make up of discrete individual quanta here. Okay, at least in principle, in the linearized theory, one can do it. Okay, and so essentially this is just exactly like quantum optics, except for now my wave consists of spin 2 gravitons instead of spin 1 photons. Okay, so this is just something one can do mathematically. Now, why this helps is because, once you have the Hamiltonian, you can actually just compute things just the same way as we do it in AMO physics. It's just an example, this is what Rothman-Bohm do, okay, look, let me take an electron in an atom. Okay, I know its stress energy tensor is essentially its kinetic energy of the system. And then I take this wave, and then I can compute something like a transition rate, like a Fermi golden rule. What's the excitation probability? Okay, let's say I go from an initial to a final state while absorbing one graviton, and I can compute this transition rate. Essentially depends on this orbitals, this electronic orbitals. So you can compute, for example, transition between a 3D and 1s, which is a spin 2 transition. Okay, you get a bunch of numbers for these orbitals, and you get something like 10 to the minus 40. So it will never happen. Okay, and exact same calculation is actually in Steven Weinberg's book as well. He had this, essentially the same calculation and the same result. He just computes what's the transition rate in the same way we do it in atomic physics, and he finds the same expression, but some 4 orders of magnitude difference here. So we apparently plugged something in wrong, but it's still, yeah. At least that's what Rothman and Bohm said. Yeah, it's interesting. I remember I gave this talk, I mentioned it to Frank Wilczek, and then he said, I'm not surprised. I don't know what you meant by that, but yeah. Sorry? Yeah, fine stuff. Because this is they're looking at the electronic transitions. So they look inside the atom. This is actually the key. But they look inside the atom, and so it just comes about from the orbitals. Like just the orbitals are defined, the transitions between those. Right. So I'll get there in a minute, right? But and so basically he says, look, needless to say, there's just no chance to observe such transition. Okay, so in other words, we can do the math, but the numbers just don't work out well. Okay, and let me just put it into like a physics perspective. And this helped me a lot to just put it like, what's the issue here? What are they trying to do? And what is the problem? The problem number one is the absorption rate is extremely low. Okay, in other words, I take an atom, I shine giant amount of gravitational waves on it, and I wait until these electrons jump. Okay, just as I do for optics. Okay, so I inside this electronic clouds, and I'm looking for this one electronic transition. Okay, that's what they're computing. This is the graviton ionization. This is the atom ionization rate. Okay, now the problem with that is you can find a cross section, and it's roughly, depending on frequency, but also on this Q. What is this Q? This is the mass quadrupole. Okay, because the gravitational waves, they don't couple to charge, they couple to mass. And in particular, they couple to the mass quadrupole of our system for gravitational waves. And for atoms, this mass quadrupole here is an electron times the Bohr radius squared. So what you get is you plug this in, and what comes out is exactly the Planck area. Okay, so what comes out as the cross-section for a single atom and a single graviton is the Planck area. And this is, by the way, quoted in so many papers. I see that's everything, like, oh, you can never detect gravitons because the cross-section is the Planck area. And that's correct for an atom. Okay, and so this is extremely small. And then, for example, okay, let's take 10 to the 50, then you get Jupiter. And this is how you get, okay, like, look, maybe if your cross-section is 10 to the minus 20, then, if you wait 10 years next to a neutron star, this is how this comes about. This is why you need Jupiter. Essentially, you have like 10 to the 50 atoms, each trying to be ionized. Okay, there's a second problem, and that is these atomic transitions, they are at optical frequencies, 10 to the 15 hertz. Okay, so there's these giant frequencies, so 10 to the 14 hertz, there's the giant frequency, and there's absolutely no sources of gravitational waves for this. Okay, so the sources that we know that exist are, below kilohertz. These are the mergers we detect. So they're really strong sources. And in this frequency range, I mean, okay, nobody knows, but there's no known sources. Okay, so this is how they get the neutron star. That, okay, imagine you're just right next to it, and it's just super hot. It will have some tail, of emission into the high frequency range. So you have two big problems with this detector. A, you look at electrons, which have the smallest mass quadrupole you can imagine, and you look at the frequencies, which are the furthest away from where a real gravitational wave takes place. Okay, and so the solution is to simply correct those things. I mean, I say simply, but the solution is that you can actually go around it. Okay, and so here, atom next to a neutron star is bad. This is hopeless. But what you could do is, what if you mimic an atom? Namely, you still look at quantized transition, but now you make it a very big mass quadrupole. Okay, and this was inconceivable even 10 years ago, but it changed recently. And in particular, imagine this mass quadrupole, you scale up to this big thing. Okay, imagine you have some big optomechanical system, okay, some acoustic resonator. Then what you get is a mass quadrupole, which is big mass, big length, okay, macroscopic, and this is much, much larger than the Planck area. Okay, so now a single graviton cross-section with this giant system as a whole is much, much bigger. It's not just simply the sum of the individual atoms. It's a completely different mode. It's not an electron moving. It is the atoms moving with respect to each other. Okay, it's a completely different mode with a different mass that comes in. And in particular, it depends on the speed of sound of this material. And just as an example, if you take 10 kilograms beryllium, what you get is something like 40 orders of magnitude larger than the Planck area for a single absorption cross-section, plus the frequencies of these acoustic ones are actually in the kilohertz or below. Okay, so that seems to be something which is nice, and that is essentially kind of the essence. This was my introduction, and right. So the next hour I'll explain how this exactly works. Yeah, right. So there's essentially three recent, really experimental advances. This has nothing to do with the theory. The theory is well understood. It really is just experimental advancements that allow us to think about the problem in a slightly different way. One is we could focus on acoustic modes and macroscopic systems, because even those can be quantum these days. And then we get really big cross-section. And of course, this is well known. This was the whole idea in the first place of doing gravitational wave detection. Okay, nobody wanted to use atoms. Of course, people knew that you have to use a big mass. Okay, that was the first idea. Okay, so we know it's a bigger cross-section. Okay, the second thing is that, we could actually look at stimulated emission from sources that we actually know, because LIGO detects them all the time. So we could cross-correlate on LIGO detections precisely when gravitational waves pass. In other words, imagine you had an atom and it would even work, and you look at your quadrupole transition, and suddenly it's there. How do you even know it was due to a graviton? You could never know. It could be any noise source. But in this limit, when we do know when gravitational waves pass, we know that nothing happens except this 1 second when the wave passed, and then it stimulates a process. It could be stimulated emission or stimulated absorption. So the stimulated one is key, and it's essentially, there's a flux of 10 to the 28 gravitons, essentially for like an average LIGO detection, which is per meter square per second. So it's a huge flux that we know when it happens. We can cross-correlate. Okay, so we know that's also true. And the third aspect that we need, and this is really the only novelty in some sense, we need to take the system and mimic it being an atom, which means that we have to zoom in on a single discrete transition of energy. Okay, we don't want to measure position or some average outcome. We really want to see a single quantum jump, just as the electrons that would jump from one orbital to another. Okay, and that is semi-good. This is actually also a recent development, not good enough yet, but it is a recent development in the last just 5 years or so, where they came to the field of quantum acoustics, where they actually do exactly that. They count phonons inside bulk materials. Here, for example, in a given Chu's lab, and there's many labs across the world, in a millimeter scale system, where they actually really can resolve individual phonons of the entire bulk material. Okay, not as an average energy, because it's not quantized, but really every individual level. Yeah, so it's these three things, essentially, if you combine them, that actually shows that, actually graviton detection is really not that unrealistic, because essentially the detector operation is different. It's in the right frequency band, and it couples much, much, much stronger than electronic transitions. Okay? The key is, though, to do quantum mechanics with these macroscopic systems, and it has not been conceivable even until recently. But now it's semi-routine. Okay, so now let me, okay, I don't have much time. I guess I have 5 minutes or so, or maybe something like that. Right, something like this. But let me just guide. I mean, the rest is just kind of adding a little bit of meat, mostly for, to convince you that it's really true. But the physical essence is all that I just said. Okay, one thing is first, look, let's compute exactly this interaction from the ground up, not assume some effective theory of this bulk, but really sum up every individual atom and how their motion is, and couple it precisely as predicted by linearized gravity. So anyway, one can do it. One has this many masses, and you can see exactly what the gravitational wave does. The essence is there's just a bunch of steps where essentially you have n atoms. Then you can change it to fundamental modes. And the essence of this is that you get an interaction Hamiltonian which has some subdominant term, which are exceptionally small, and they're essentially individual atoms in their own local traps, so they barely feel gravity. It's very similar to this electronic transitions. However, you get collective modes where it's really the relative motion of all these atoms with respect to each other, and that scales up with mass and length of the system. So this is the enhancement mechanism. This is precisely the one that gives you a larger cross-section rather than all the individual atoms. So it's this aspect that we want to kind of zoom in. And then you can look at, okay, look, what is the transition rate? For example, you can find in the similar spirit, you can find what's the stimulated transition rate. And what's interesting, this is well known. This is, again, even in the 60s in textbooks and papers where we know what the stimulated emission rate is. And as an example, if you had, say, like if the Weber bars work, just as they envisioned, and imagine we had this, LIGO detection of this, the first detection with this amplitude. And we had this aluminum bar. If you just compute what's the stimulated emission rate, what comes out is on average roughly 1 hertz, which means that these resonant detectors, even as envisioned, if they ever worked, they actually would operate on average something like they would exchange just 1 graviton on average per second. So in other words, if you had a resonant detector, because gravity is so bad, it's so weak, you actually get automatically in this limit where you're just kind of on a single particle level, where really if you absorb anything, it's just so unlikely, but if you absorb anything, it really is just 1 or just a few gravitons. Okay, so this average rate. Now the key point though is you have to zoom in on a single event. This doesn't tell you anything. The point is just to say, hey, within a second there's only one exchange. Can we zoom in on just one event of single quantized, essentially it's essentially a conversion. One gravitational wave passes, and then 1 graviton is converted into 1 phonon. Okay, can one zoom in onto this event? And one can, and for that, I just want to say this it's the analogy is, that's what the photoelectric effect essentially does. It's like there's a bunch of classical light bulb photons coming in, and then you really absorb just a discretized amount of energy, and this is kind of the key. And by the way, why I'm mentioning this is every photon, not every, but most photon detectors you buy today do just that. Okay, they never do anything more advanced. They don't. It's not like inside there's a Bell inequality test. It doesn't tell you more than just simply one absorption of just 1 quanta of energy. Okay, this is the definition of a particle detector. So I just want to say this is by definition a particle detector, and that's exactly what you buy off the shelf. And so this is still the same principle. Now here, how do you do it? Because you have these discrete levels, and the trick is resolving quantum jumps. Okay, and so essentially you want to resolve a single quantum jump and herald only on that, not average over many energies. And for example, this was recently done by Michel Devoret's group, who just got the Nobel Prize, not for this, but maybe also a bit. But it's a beautiful experiment where they essentially can, really they call it catch and reverse a quantum jump mid-flight. So they do that with superconducting systems, and one can also do it with acoustic systems. So it's being able to really resolve a single jump. And so that's the capability one needs just for these acoustic modes. And what I want to say is that something very similar has been done now over the last 5-6 years or so in different labs, where here, for example, you have here like a piezoelectric coupling where you can resolve individual phonons in Konrad Leonard's group, okay? Or here in Yuven Chu's lab, here, for example, as well, they can really measure 0, 1, 2, 3 phonons. They can really distinguish them. You need a nonlinear coupling. You need a nonlinear measurement. It's non-Gaussian. You have to do some nonlinearity. It's not a position measurement, but they can resolve it at these small scales, okay? Or you can also do it with superfluid as well. Here in Jack Harris's group, for example. So just to say that this is actually experimental capability, just not there yet in the scales we need. And now let me just mention, okay, what are the scales you need? We just basically looked at, okay, now this gravitational wave physics is more complicated. It chirps, you can't just integrate to infinity, but you can solve the problem exactly. And what you find is that, oh, look, we can maximize the probability of just a single detection. Let's say we don't want to have a good detector. We just want to maximize the probability of only one quantum jump. Then we find the ideal mass for the system, which depends on the, material, but it also depends on the profile of the gravitational wave. So this chi is, this one-sided, finite transform. It depends on gravitational waves. Then we looked at what about all these different gravitational waves we already observed, and this is a little bit daunting table, but I just want to say here, this first couple of columns are just different waves we just looked at, black hole mergers and so forth, and then this further down is some speculative sources at high frequencies. So it's not so important. But the thing is that even for gravitational waves we observed, it turns out it's way too difficult to absorb a single graviton, except. So you need like something at ton scale resonators, except for one type of source, and that is the neutron star mergers that have been observed. And that's because they last much longer and are a bit closer. And so for these systems, it turns out if you had something like a 15-kilogram resonator made out of beryllium and cooled to about 1 millikelvin, then this system would really be able, if that was operational, would be able to, in parallel to LIGO detection, would extract with the maximum probability one single quanta out of the passing gravitational wave. So this would be a detector which is really, it's not easy, but it's not unreasonable either. Okay, so these are all completely reasonable numbers. The main point is that you have to do quantum acoustics with this 10-kilogram resonators, and right now they do it at like gram scale. Okay, so you have to do quantum sensing better. But you don't need any quantum superpositions or other crazy. You really just need ground state cooling plus sensing. It's easy. Plus, I want to say, okay, so the key is that you really want to look at discrete exchange of energy, but it doesn't even have to be an acoustic resonator. There could be many different systems. In fact, there have been some other, the key point is you want this large mass quadrupole, and there have been some alternatives proposed as well. For example, axion conversion, which you can also convert a graviton and an X-ray, but at very high frequency. So if you had sources there, it would work. There's now just, I think last week was a paper saying, oh, we could rotate interferometers, and this could also be a way to convert gravitons into photons. And I want to mention, especially here, that in principle, if you had resonant operation plus energy measurements, then exactly the same would happen in LIGO. You would just simply count gravitons. The resonant part is important only for the interpretation, because the resonant part tells you that resonantly, the energy must come from somewhere. So if you see a click and it's resonant, then it must have been that this was a single graviton absorption event. Okay, if it's off resonant, then the energy does not correspond to a graviton. It's a different thing. So this is the thing. But in principle, so I feel like so I'm very positive. I feel like this should be possible within 10 years. I hope at least. Okay, but now finally, I just want to say, okay, I know I ran out of time, but a very important point. This is just a summary. Yeah, you can do it. You piggyback on LIGO detections, and then in principle, you kind of mimic this photoelectric measurements with quantum sensing, and so Dyson was right about everything except this one part where he scaled up. You shouldn't look at electronic transitions, you should look at other transitions. And you basically test this, this formula for gravitational waves. Now, I do want to say that, okay, there is some interesting things you can learn. For example, there's some papers by Frank Wilczek in my previous postdoc, and also we have a paper now coming up where we just show, look, you can characterize some interesting things about gravitational waves actually with these click detectors. You can characterize Gaussian quantum states, but you can also have some conceptual input on linearized quantum gravity from such detection. But there is a caveat, and the caveat is that I want to really highlight that detecting gravitons, it does not mean you prove the whole glory of quantum physics. This is because the same clicks in principle could be reproduced by some semi-classical models. Okay, so if you really don't want to quantize gravity, you could live with it even when you see these clicks, if you had some kind of stochastic interaction here. Okay, so this means that this, just as the photoelectric effect alone is not a full proof of the full quantum theory. However, you know, for that you would need, you know, more like measuring anti-bunching or something like that. However, it's also, this model is not classical wave physics. So I want to say that there's a little bit of a misconception. This semi-classical model is not what classical wave physics predicts. That was precisely Einstein's insight, that classical wave physics will never give you threshold behavior plus this frequency behavior and then intensity scaling. Instead, this is an artificial test model which doesn't conserve energy, and it's just a test model that came up after we knew everything about QED. Just somehow, hey, can we be even more certain? Okay, so this came up in the 70s, long before everybody already accepted the existence of photons. So this is not the benchmark to rule out this model. It would be nice, but this is not something that comes out from normal physics. Okay, and I just want to say again, like every single photon counter essentially just does precisely this click detection. It does not do anything else. Okay, and then I think I ran out. I wanted to give this. Yeah, okay, maybe let me give this very quick analogy, just also that the input state is also irrelevant. There's often this thing like, oh, yeah, but it's just a classical wave. Yes, it is, like for any detection. You know, if you shine a light bulb on a photon detector, it still detects a photon. So it's a little bit like this, that you have a classical giant wave. Okay, it's in a coherent state, like nearly infinite energy. And then it's actually made up maybe of this huge number of quanta. And what this detection does, it extracts just one quanta out of it. Okay, so it's essentially, can you have a net which just picks out one atom out of this giant wave? Okay, even though the wave is still classical. And that's precisely what this detector does. It just takes out one quanta of energy out of this giant wave. This is precisely what this discrete transition is. And the point of Einstein 1905 was precisely that this behavior cannot follow from wave physics. It is not possible. Okay, you know, and that's, for example, here this beautiful Millikan experiment where he showed us thresholds and then kind of an increase with intensity. This is precisely this photoelectric prediction, which Einstein got the Nobel Prize for. However, later it was realized, oh, you could have some weird semi-classical models that could repredict it, but they're harder to rule out. But they're not, you know, they're not energy conserving. They're not a limit of normal GR. They're not wave physics. So in other words, this detector is really a bona fide particle detector. Okay, so and then finally, I just want to say you could learn. I mean, this is really my last slide. Really. I just want to say now. Okay, there's certain models you can't rule out, so you need more experiments, and that's great. But there are certain questions you can ask about linearized quantum gravity, and we came up with a few very simple ones. Okay, because I don't know the limit of, I don't know, whether string theory would be different in loop quantum gravity, probably not in this limit. But there are certain other just phenomenological questions you can ask. For example, essentially you're probing this interaction Hamiltonian. And you can ask, for example, the following question: do we even know that E equals HF is correct for gravity? And we don't know that. What if your Planck's constant was different in the gravitational sector? That would be fully consistent with all classical detections, but somehow you would get suddenly, like, you know, you would get a double transition instead, or some, you know, like you would have a bigger chunk. Okay, so maybe H bar could be different and you would be able to probe it. Okay, it could be maybe not universal. Then there's another question, namely, the theory predicts stimulated emission and absorption are exactly equal rates. Okay, so you could do exactly the same experiment with detecting or emitting a graviton, stimulated emission. You can do that and then see if the rates are equal, which should be true in normal quantum theory. You can also test if it's actually a spin 2 transition, a single particle, because there are certain transitions just as an atom that will be forbidden and certain that are allowed. Okay, and the same you could probe whether this really carries a single quanta of angular momentum, spin 2. And then, of course, you know, the interesting thing is maybe you can combine it with other experimental input and really get much better picture on linearized quantum gravity. Okay, with that, I apologize that I went over time. Just want to say that the bottom line is it is possible to detect. It really just means to detect one quantized amount of energy. It can be done. It's not easy, but it's also not, it's not that hard in principle. So I think it could be maybe done within a decade. And it has been overlooked simply because of the experiments weren't there yet. Like the traditional focus was always of what is the most quantum system, and that's an atom. Okay, and for an atom, it's just really bad. But now that we have macroscopic systems, we can think about quantum mechanics. The game changed. Plus, with LIGO detection, where we know where these systems are. Okay, and it can test some aspects of linearized quantum gravity to probe it. Very much similar spirit to like the early days of quantum theory of 1910s or so. Okay, so it doesn't tell you the full glory of quantum theory, but can probe small aspects. Okay, with that, thank you very much. And I want to thank my group and thank you for your attention.
You can take a few questions for Igor. One way up here.
Yeah, I was wondering if you had to cryo-cool something like a mechanical oscillator to like really Kelvin temperatures. I imagine there's a ton of background vibrations at kilohertz. And is that something that experimentalists could control easily? And also the second question is, can they also maintain like a long outtimes to catch a gravitational wave then?
Yeah, these two questions are related, and thank you very much. I didn't show it here. You're exactly right. So the question is, okay, how well can we actually exclude other noise sources, and for how long have we do it? So these numbers I showed with the 1 millikelvin and Q 10 to the 10, this assumes, or they're not assumes, but this basically tells you that what we assumed is that the neutron star merger lasts about 4 seconds. And so we assume, let's say you want to keep your system free of thermal excitations for about 100 seconds. Okay, something like that. So, a factor 10 or even more, bigger than this window. And for that, you need precisely this Q factor 10 to the 10 and 1 millikelvin that tells you that within you shouldn't get any excitations within 100 seconds or something like this. But it's actually even less daunting because you could live with worse Q factor, essentially with a bit more thermal vibrations, precisely because you exactly cross-correlate with LIGO. So you have, here you maybe have a duty cycle. Essentially, look, you ground state cool your system, you measure, and then after 100 seconds, okay, it gets excited, let me measure again, and so forth, until you get a call from LIGO and say, hey, we just have a neutron star merger the second, maybe it's through post processing, but still, and then you're like, oh, you know what, in this window, I exactly saw one jump. And so you have to keep running. Or even better, if you have like Lisa that will tell you beforehand, like, you know what, in 1 week, there should be something in your detection window. But yeah, what you say is exactly right, and this is challenging for some materials, but that's why this beryllium, for example, at 10 to the 10 Q factor should be sufficient to suppress this thermal vibration for this short time window. And then you just have a duty cycle where you recool.
In regard to this analogy to the photoelectric effect, it seems important to me that the free electron has a continuous spectrum. You can sort of get this plot, right, with the energy deposited scaling frequency. So is there some way that you can imagine using the mechanical detector to show that same relationship?
That's a good question, especially with this linear part. Let me first say one aspect to it, namely, yes, it usually is a continuum. And then the reason that you know that it's a discrete amount of energy is that there is some kind of maximum kinetic energy that comes out. So it's measured by voltage. So there is some kind of maximum energy that comes out into the continuum, which is precisely this E equals HF. That's kind of this threshold amount, that it can never be more. So they essentially use the continuum is not essential. Rather, what's essential is to see, can we see somewhere this discrete amount of energy? And they can see it on the stopping voltage. Okay, so the stopping voltage gives you this discretization. Here in this bound system, the discretization is given kind of for free for you in your detector. It is already discrete. However, the second aspect about this, that it increases linearly, that I think you would probably need to look at. So you need to see basically how much energy is deposited as the intensity goes out. So you have to probably monitor how much energy is pumped into the system. So like some higher higher modes. So I'll have to think a little bit about it. Or you have maybe many detectors. So this linear scaling is maybe that's a little bit, I think you can basically dot it out with some discrete parts that somehow, oh, look, nothing happens. Then if you increase frequency, there will be actually, you know, like now there will be a bigger energy. So imagine you have like, I mean, just conceptually, imagine you have like 10 detectors, each at different frequency. Then you should, oh, the wave shouldn't excite anybody. And then once it reaches the threshold frequency, it will be, you know, higher and higher energy. So other modes will get excited. But I just want to say for the discretization of seeing the discretization, the continuum is not essential, but, you know, you extract it from that.
So, Igor, suppose we detect a graviton like you described. There will be a party. I hope I'll be invited. But after all the cake and ice cream is well, you said there are some things we can test, you know, like the universality of H bar. But suppose you look ahead, now we're routinely detecting single gravitons. So do you foresee that will open a rich experimental frontier? Wonderful things we'll be able to do with our single graviton detector?
It's a great question. I think a little bit. I think, yes, I think you could do a little bit more. You can even put input, you know, like, hey, you can maybe, you know, just, you know, maybe you could do tomography, like better, like quantum state tomography of the incoming waves. You can combine it with the regular measurements. So there is some kind of advantages. You can do sensing. For fundamental physics, right, so let's say you see everything works as expected and there's no surprises. Like, where do you go next? And I think that's a very good question, but for me, the inspiration is, again, a little bit the early days. So how they went is they went through many experiments, many different ones. So they had the Planck spectrum, they had the photoelectric effect, they had the Compton effect, you know, many others. And so somehow something similar probably, I don't know how, but something similar would be nice. Namely like, okay, so this is maybe one window. Can we conceive maybe something similar from other aspects? So I think it would be a little bit helpful even for metrology, but for fundamental physics, you probably would then have to go to the next experiment, next ideas.
And a lot for theorists to think about.
Right. So it keeps us busy.
Okay. Well, we're now going to have the reception on the patio at Bridget Annex, where we can celebrate today's talk. And let's thank Igor one more time.
Yes.